September 1916. A British soldier crouches in a trench on the Somme, holding a finned projectile weighing 11 pounds. He drops it tail first into a steel tube angled at 45 degrees. The projectile slides down. A firing pin at the base of the tube strikes the propellant cartridge. The mortar fires with a dull thump. 3 seconds later, the bomb detonates in a German trench 80 meters away. The soldier reloads immediately. No complex aiming calculations, no hydraulic recoil systems, no training beyond understanding that the bomb goes in tail first and gravity does the rest. He fires again and again. Within 1 minute, he has launched 15 bombs. The tube weighs 49 pounds. The entire weapon system can be carried by 3 men and assembled in under 30 seconds. It requires no foundation, no recoil pit, no specialized crew. A week earlier, this soldier had been a clerk. He had received 4 hours of training. He could now deliver high-explosive munitions at rates approaching light artillery, and he could do so from positions where conventional artillery could not operate. The weapon was the Stokes mortar, and within 18 months of its introduction, it had rendered obsolete every heavy trench mortar design that preceded it. The British Army entered World War I with a mortar problem that was doctrinal and technological. Trench warfare created demand for high-angle fire weapons capable of dropping explosives into enemy trenches from short range. Existing mortars were adaptations of obsolete siege weapons or improvised designs using modified drainage pipes. The standard German Minenwerfer was effective but weighed over 200 kilograms for the light version, required a prepared emplacement, and could manage perhaps 2 rounds per minute under ideal conditions. British forces initially deployed various expedient devices, including catapults and converted steel cylinders, none of which were satisfactory. What infantry commanders needed was a weapon that could be man-portable, that could fire from unprepared positions, that could deliver sustained rapid fire, and that could be operated by soldiers with minimal technical training. The specifications seemed contradictory. Weapons delivering useful explosive effects required substantial propellant charges that generated recoil forces demanding heavy construction and stable mounting. Rapid fire required simple mechanisms, but most simple designs could not handle the stresses of repeated firing. Portability demanded light weight that conflicted with structural strength requirements. The solution came from an engineer with no formal military weapons experience. Wilfred Stokes was a civil engineer and inventor who had designed various industrial equipment, including railway components and mining machinery. In 1915, he approached the War Office with a mortar design that violated conventional artillery engineering principles. Rather than absorbing recoil through mass and mechanical systems, Stokes proposed transferring most of the recoil force directly into the ground through a baseplate. Rather than using complex breech mechanisms and loading procedures, he proposed a design where the projectile itself contained the propellant and the firing mechanism was simply a fixed pin at the tube's base. Rather than requiring trained crews to calculate elevation and bearing, he designed a weapon where range was controlled primarily by tube angle and propellant charge selection. The War Office was skeptical. Stokes built a prototype at his own expense and conducted demonstrations at Lille Barracks in Aldershot in early 1915. The weapon worked. By June 1915, it was in production. The Stokes mortar consisted of 3 components. The barrel was a smooth-bore steel tube, 3 inches in internal diameter, 51 inches long, weighing 22 kilograms. The baseplate was a circular steel plate approximately 430 millimeters diameter, weighing 17 kilograms, with a socket to receive the barrel's ball joint. The bipod was a collapsible steel frame weighing 10 kilograms, with traversing and elevating mechanisms allowing fine adjustment of tube angle. Total system weight was 49 kilograms, light enough for 3 soldiers to carry over difficult terrain. Assembly required inserting the barrel ball joint into the baseplate socket and attaching the bipod to the barrel's middle section. No specialized tools were needed. Disassembly took approximately 20 seconds. The ammunition was equally simple. The bomb was a finned projectile with an ogive nose containing approximately 1 kilogram of high explosive. A central tube ran through the bomb's body containing the propellant charge and a percussion cap at the base. 4 spring steel fins at the tail provided stabilization in flight. Total weight was 4.5 kilograms for the standard high explosive round. To fire, the operator dropped the bomb tail first into the muzzle. Gravity accelerated it down the tube. At the bottom, the percussion cap struck a fixed firing pin mounted on the baseplate. The propellant ignited, generating gas pressure that drove the bomb up and out of the tube at approximately 75 meters per second. The recoil force drove the baseplate into the ground. The tube and bipod absorbed minimal stress, allowing lightweight construction. The range with a standard propellant charge was approximately 700 meters. Reducing the charge by removing propellant increments decreased range proportionally, allowing precise adjustment without changing tube elevation. The rate of fire was the weapon's revolutionary characteristic. An experienced crew could sustain 20 rounds per minute. The limiting factor was the physical effort of dropping bombs into the tube and the availability of ammunition, not any mechanical cycle time. This rate of fire exceeded contemporary field artillery on a per-tube basis and was achieved with a weapon requiring a 3-man crew rather than 6 to 8. The high angle of fire meant the Stokes could engage targets in trenches, behind ridge lines, or in defibrillated positions inaccessible to flat trajectory weapons. The relatively short range was acceptable because trench warfare occurred at close quarters. Most targets were within 500 meters of friendly positions. Operational deployment began in mid-1915 with initial batches issued to infantry battalions on the Western Front. Operational reports were immediately positive. The weapon's portability allowed it to be moved forward with assaulting infantry, providing direct fire support impossible with towed artillery. The rapid rate of fire allowed single mortars to deliver suppressive barrages previously requiring multiple guns. The simplicity of operation meant casualties could be replaced with minimally trained soldiers without significant loss of effectiveness. By early 1916, demand exceeded production capacity. Additional contractors were brought in. By the Somme offensive in July 1916, British forces deployed hundreds of Stokes mortars across the front. Tactical employment evolved rapidly. Initial doctrine treated mortars as defensive weapons for counter-battery fire against German Minenwerfer positions. Experience demonstrated that massed mortar fire could suppress enemy trenches more effectively than preliminary artillery bombardment in many situations. The weapons could fire from forward positions, reducing the time between fire order and impact. They could shift fire rapidly to new targets without the delays inherent in redirecting artillery batteries. Observers reported that sustained Stokes mortar barrages created psychological effects disproportionate to the actual explosive tonnage delivered. The high rate of fire and unpredictable impact points made trenches untenable during bombardment. Comparison with German and French mortars illustrates the Stokes design's advantages. The German 7.6-centimeter Minenwerfer was accurate and powerful, but required a 4-man crew, weighed approximately 150 kilograms with its mounting, and achieved perhaps 3 rounds per minute. The French 58mm mortar TN No. 2 was lighter but less powerful and mechanically complex, with multiple loading steps and a lower rate of fire. Both designs utilized separate propellant charges, requiring careful loading, which introduced delays and potential errors. The Stokes design, with its self-contained propellant and drop-fire mechanism, eliminated entire categories of handling errors and mechanical failures. No other combatant produced an equivalent weapon until late in the war, when both German and French forces developed direct copies of captured Stokes mortars. There were limitations. The smoothbore barrel provided no spin stabilization, making the bombs vulnerable to wind drift and reducing accuracy compared to rifled weapons. Effective range was limited by the relatively low muzzle velocity required to keep recoil forces within the baseplate's absorption capacity. The thin-walled barrel could not sustain fire indefinitely. After prolonged rapid fire, the tube heated enough to affect propellant burning rates and occasionally cause premature detonations. The baseplate required relatively solid ground. In muddy conditions, it would dig in progressively deeper with each shot, changing the tube angle and disrupting aim. Crews learned to position boards or wooden planks under baseplates in soft terrain, adding setup time and complexity. The weapon's very simplicity created unexpected problems. Because anyone could operate it with minimal training, commanders sometimes assigned mortars to inexperienced personnel who lacked an understanding of indirect fire principles. This resulted in incidents of short rounds falling into friendly trenches. The high rate of fire encouraged profligate ammunition expenditure, straining logistics systems unprepared for the consumption rates. Several documented cases exist of units exhausting their mortar ammunition allocation within the first hour of an engagement, leaving the weapons useless for the remainder of the operation. Production continued through the war's end. Approximately 10,000 Stokes mortars were manufactured by 1918. The design was standardized as the 3-inch trench mortar Mark I and remained in British service through World War II with only minor modifications. The fundamental design principle, drop-fire ignition from a smoothbore tube supported by a baseplate, became the template for virtually all subsequent mortar designs worldwide. The U.S. M2 mortar, adopted in 1940, was a direct descendant. The Soviet 82mm mortar used identical operating principles. Modern infantry mortars, including current 60mm and 81mm systems, are evolutionary refinements of the Stokes design rather than fundamentally new approaches. The concern that terrified some military commanders was not the weapon's effectiveness, but its implications for military hierarchy and specialization. Artillery had historically required years of training, mathematical education, and technical expertise. The Stokes mortar could be taught to a minimally educated infantryman in an afternoon. This democratization of indirect fire capability threatened institutional structures built around technical specialization. Staff officers who had spent careers mastering ballistic calculations and gunnery procedures found their expertise made partially obsolete by a weapon that required mainly physical coordination and basic judgment. The resistance was never formalized as policy, but appeared in procurement delays, in reluctance to expand mortar allocations, and in attempts to impose complex operating procedures that negated the design's inherent simplicity. The soldier on the Somme who fired 15 bombs in 1 minute did not consider the institutional implications. He understood that the weapon worked, that it killed effectively, and that it kept him alive by destroying enemy positions before they could respond. The Stokes mortar was never elegant. It was a steel tube, a baseplate, and a bipod. It required no sophisticated understanding of internal ballistics or trigonometry. It simply functioned exactly as designed, delivering high explosive munitions at rates and from positions that conventional weapons could not match. The generals who feared its simplicity were correct to be concerned, though not for the reasons they articulated. The weapon demonstrated that technical complexity was not inherently superior to functional simplicity, and that lesson would echo through military procurement decisions for the next century.